The introduction. So I'm Anthony Lin from Oxford University, and this is a joint work with my co-authors from other institutes in the UK and China. So strings are an important data type which are prevalent in today's software. In fact, virtually every web page, as you already saw on the previous two presentations. So for example, on my LinkedIn friends list, each friend actually corresponds to an HTML hyperlink, which when clicked, will invoke the function viewPerson, which with his or her name as an input. So such an HTML page is typically dynamically generated by a series of string manipulations, whose resulting strings will be inserted into the page. And many bugs could arise in this way, some of which are hard to find by existing testing and verification methods, some of which are have important security consequences. So for example, one potential bug in the above piece of code is whether it's possible to insert a dangerous HTML element of this form, which when clicked will invoke the malicious attack script in addition to the function viewPerson. So this is an example of bugs known as cross-site scripting, usually abbreviated XSS. And a standard industry defense against XSS is to sanitize the input name by means of character escaping, which we see on the first two lines of the code. So for example, HTML escape converts reserved characters to corresponding HTML characters. And so the question is whether the resulting program is safe, that is whether there's an input that leads to name element matching the attack pattern. So in order to discover such bugs, many program analysis and automated testing methods, for example, like symbolic execution, typically resort to string theory. I'm not talking about physics, of course. I'm talking about constraint solving over the string domain. And the setting of such a string theory is typically as follows. You have constants and variables over the string domain, typically over a finite alphabet. And you include string operations like equality, concatenation, regular expression matching, etc. And constraints or formulas are typically quantifier-free, first-order formulas, which means that you simply close your basic statements over string operations, constants, and variables, just using by Boolean combinations. And the problem you're interested in is satisfiability, that is to check the existence of a solution. So here's a little example. I don't know if you can see it. It's a bit too small, but so here I use. So this is an example of a constraint, and I use x and y as variables, and I use magenta colors to indicate string constants. And for this example, and remember, plus is concatenation. Yeah. So this is if you check carefully, this is satisfiable by assigning b to the constant b to x and empty string to y. Okay. On the other hand, so this is an example of an unsatisfiable constraint. So you have the same constraint, but you assert that x matches a star. Okay. So this is an example of regular expression matching. We also call this regular constraint. And notice when I say regular expression, I always mean regular expression over the string constants, not variables. Yeah. Okay, so what do we know about string theory in practice and in theory? There have been many string solvers developed in the past 8 years alone. I'm trying to list them here, but disclaimer, this is a very impartial list, and do not shoot me if your solvers do not appear here. So the focus typically for string solvers, practical string solvers, is pretty much on heuristics, and they rarely use complete algorithms that are developed in theory. Why? Well, because unfortunately there's just still lack of fundamental understanding of decidable string constraints. So let me tell you a little bit about this. So for example, so a classic decidable string theory is this quantifier-free theory of concatenation with regular constraints. So some examples of the constraints we already saw in the previous slides. Yeah. So in this case, this is known to be decidable by a series of work, but the main result is the result by seminal paper by Macagnin in 1977. However, concatenation, regular constraints, these are only two string operations. There are many other string operations that are quite important in practice. So for example, what if you want to extend this with length constraints? So here we have this additional constraint, as you see here, length of x equals length of y. Okay, so this is currently a long-standing classical open problem. It's been open for 50 years, as far as I know, and there are many such problems actually in regarding string theory. To make things worse, many string operations are still missing in the theoretical study of string theories. And yes, so one such function is the ReplaceAll function, by and large missing both from practical string solvers and also from theoretical studies of string theory. And the goal of the current paper is to investigate decidable ways to add ReplaceAll to string theories, okay, which I will tell you a little bit more in the next few slides. So, okay, so I've talked about ReplaceAll function, but what is it? Well, it has 3 input string parameters, as you can see here. So there you have subject, pattern, and replacement strings. And the output here is simply subject with all occurrences of string matching pattern replaced by the replacement string. Okay? And I mean, if you use Vim, you've seen this thing. You know, you've really used this actually. So for example, you can write things like that. That's so here is a little example. So suppose you suppose this is subject, which is too small to see, but this is intentional. That's not a problem. Suppose the pattern string is 2 and the replacement string is 3. Okay. So in order to obtain the output, what you do is that you first identify all occurrences of 2 in the subject, which are here. Okay. And what you do next is to just simply replace them by 3. Okay. So basically you get that. Okay. So and you can write it like that in Vim. Okay. So there are 2. So that's ReplaceAll, but apparently they can be also used to. They have several applications. So here's one. So it can be used to express sanitizers for web applications as string constraint. So the string constraints required for expressing this kind of functions. So for example, in this piece of code here, HTML escape converts the string on the left here to the string on the right here. Okay, so by simply converting them to the corresponding HTML characters. So the inner HTML does the reverse operation. Okay. And what about escape string? Well, this is something that you've seen as well. So it's simply / escape single and double quotes in the input. So you can see here. So the single, you get the / there. Okay, so that's first application. Second application is another application is to express string operations in HTML templates like mustache.js. Okay, so in Mustache we separate. Instead of having a single HTML document, what you do is that you separate the data from the document, okay, from the skeleton, okay. So here, for example, you can have a template that looks like this, okay, and here you have the holes here, bio, and you have the data mentioned here separately, okay. And an HTML document can be generated by instantiating certain strings, like for example bio here, with the corresponding data in the JSON file. Okay, so that's an example. Of course, you can also use other JSON file. For example, this is another example of a JSON file and bio, and you can generate stuff like that, which is actually it turns out to be vulnerable to cross-site scripting. All right, okay, so that's these 2 applications. And all right, okay, so we know now how ReplaceAll function work. How do we add this to string theory? Well, it means that we allow this kind of formulas here, this kind of atomic formulas, okay? So in our constraint. So firstly, X here, of course, is so X subject, pattern, and replacement. So this can be either string constant or variable, whereas the pattern here can be a general regular expression over string constants. Okay, and there are many different semantics, but what we use in the paper is typical semantics used in some languages. For example, like leftmost longest match. Okay, but don't worry too much about this. This is more like details. And Okay, so that's the that's how you do that. How you add this replace all to string constraints. And the most common usage is okay. So we have different combinations here, right? So but the most common usage turns out to be that the pattern and replacement strings are actually constant strings. Okay, so here's an example. So we have this escape string before from the previous example, and you simply replace all occurrences of double quotes and quotes by backslash double quote and backslash quote. Okay, so this is what you do, and that's this matches the this common usage. And this is not the not so uncommon usage is that the replacement string is a variable. Okay, it's not a constant, but it's a variable. So and the pattern is a constant still. Okay, so this is the example from Mustache. So you can see here, so you're going to replace all occurrences of bio with the corresponding data, which is not available a priori. And also the same with other holes like username, okay? All right, so that's replace all in string theory, but it turns out, unfortunately, that replace all is a very powerful operation, and adding it naively to string theory results in undecidability. So in fact, you only need the following things: equality, regular expression, and replace all with the most common usage, okay, pattern and replacement constants, to be undecidable. There's no concatenation at all here, okay? So this can be shown by an easy reduction from PCP, but I'm not going to go through that here. So this is so here's an example, but the corresponding formula looks like this. Okay. So, but I mean, roughly speaking, what it does is you just simply guess the sequence of indices, and then you want to replace the index with the corresponding top and bottom strings. So that's roughly how it works. And at the end, you just try to match the top and bottom strings. Okay. It turns out there's to get decidability. There's the good news is that there are some ways to get decidability, and that are in fact applicable to symbolic execution of programs. And this is the straight line fragment framework of from this previous work. Sorry. Oops. Okay, and this constraint language is best described in terms of symbolic execution. Okay, so and I will describe this in terms of symbolic execution here. So firstly, what you do is that you consider a symbolic execution in a program. So basically, you have a sequence of assignments and conditionals or assertions. Okay, and you consider the problem of path visibility, which is to decide if there exist input strings that satisfy all the assertions. Right? So it turns out that decidability can be obtained for path visibility whenever the assignments only applies concatenation. That is here you have concatenation of string constants and variables, or finite state transducers. Okay. And which I will not define, which will be defined in the next slide. But the important thing is that it can also define the replace all function where the pattern and replacement string are constants. And the assertion here are just given as regular constraints. And the crucial thing here for the decidability is that there is no general string equality in conditionals. Okay? So just to take a look at a simple example. So here is simple symbolic execution. And it turns out path visibility is simply satisfiability of constraints in disguise. And here's the corresponding formula, the formula corresponding to the symbolic execution, which you simply obtain by introducing a new variable each time you have an assignment. Okay. And this is also known as static single assignment form. So why straight line programs? Why straight line fragments? Well, so firstly, it prohibits bad formulas. So this is the formula that we get from the undecidability that we saw in the previous slide. And as you can see here, there's this equality check, and this kind of stuff is eliminated if you consider straight line constraints. And secondly, the fragment also captures constraints from symbolic execution in practice. For example, if you look at this example here, so that we saw on the previous slide. Okay, so and what you want to do at the end is that you want to finally you want to check if this matches some attack this regular expression here. So this also matches the. This also belongs to the straight line framework. Okay, and there are also other lots of other existing benchmarks that are in this straight line constraint asterisk. Okay, however, this straight line fragment cannot express some constraints that we saw, for example, here, the mustache example, because you do need to have a more general use of replace all. Okay, so where the replacement string is also a variable. Okay, so our main result here is so we have a more expressive decidable straight line fragment with replace all that addresses the limitation on, that I mentioned on the previous slide. So more precisely, we show that path visibility is still decidable, even when we use the more general usage of replace all, where the pattern is a regular expression and the replacement string is a variable. So this can model the examples that I mentioned on the previous slides, but can also model examples from auto-sanitization in web templates, for example, that are commonly used in Clojure, Angular, Handlebars, etc. Okay. So this decidability was surprising to us because it turns out that arithmetic can actually be simulated here to some extent. So, for example, you can simulate the number 5 here as a sequence of A's. And multiplication can be expressed like this by replacing all occurrences of A and X by Y, and addition can be simulated by concatenation. Okay, so I will tell you a little bit about the proof idea very briefly. So the first thing that you do is that it turns out concatenation can be made syntactic sugar. That is, it can be expressed just in terms of replace all. So, for example, if you have this equation, you can turn that into this, okay? And what you do here is that you simply introduce new constants, lowercase y and lowercase z, okay? And what you do next is you want to replace all occurrences of this lowercase y and lowercase z by the corresponding variables. Okay, so just very quickly, so the proof idea is the most important idea here in our in the proof here is the notion of a pre-image of a language under replace all with a fix. The pattern here is fixed. Okay, and this is defined as follows. So it's basically simply a pairs of. So it's simply a pair of contains pairs of subject and replacement strings, which map to a string in the language L. So here is a little example. Suppose L is the following regular expression, and the pattern here is just 9. Okay. So this pre-image is actually a complex set, but let's go through some of the examples here. So, for example, if 9 does not occur in V, that is, does not occur in the subject, well, then you don't actually have any. So the subject can match anything in L, and the replacement string can be anything. Okay. Now, what about if the subject here is 9 is a nice name? Well, then in this case, the replacement string has to match the pattern here in the pattern here. Okay. And this is the more interesting. The case that is more interesting, I think. This is hi 9 is a nice name. So in this case, the replacement string has to match both the pattern from here, the first occurrence of 9, and then the pattern from the second occurrence of 9. Okay. And there are many other combinations, but it turns out that the cool thing is that this pre-image can be described in a finite way and finite and regular way. Okay, so this is captured by the notion of recognizable sets. It's simply a finite union of products of regular languages. Why does this imply decidability? Okay, so basically it implies decidability by what you do is that you simply keep applying this to the last occurrence of replace all. Okay, so for example, in this case, you apply this on L2, and then you remove replace all. Okay. and then you get this, you basically take one of the product, and then here is, let's say, S and S prime, and then this contributes to the, so you replace this by this new regular constraints, and you keep doing that all the time, okay, to the last occurrence of replace all, and finally at the end you just get conjunctions of regular constraints, okay? And the good thing is that these are decidable. Okay, so I'm not going to go through the proof idea of the lemma, so I will just refer you to the paper because of time constraints. But I want to mention quickly about the complexity of the algorithm is exponential space, and there's currently a gap here between p space and exponential space. Okay, that's the base lower bound. Okay, and finally, I just want to mention two simple extensions, and the first one is length constraints. This is unfortunately undecidable if we include length constraints in our constraint language. And secondly, what if the pattern is a variable? That's actually not a very common usage, but that also turns out to be undecidable. Okay. All right. Okay. So as final words, I just want to summarize quickly. So we've delineated the decidability boundary of string solving with replace all, and we believe that there's a reason to be optimistic. So there's just several ongoing work at the moment, which is the computational complexity issues. So there's a gap between exponential space and polynomial space, and there's also the other work that, for example, try to unify transducers and the ReplaceAll function. And finally, we've also implemented a prototype of string solver based on our constraint language, and you can find it here. Thank you so much.
Okay, we'll start with a question from the internet while folks line up at the mic. So have you explored any other operation besides concatenation that can be simulated by ReplaceAll? And I guess we saw a couple on the extension side, but are there additional string operations that you guys are interested in?
Yeah. Okay, so other things that can be simulated by ReplaceAll. Yeah, so I mean, that's a very generic question, but
feel free to riff on it.
Yeah, so okay, I mean, like, if somebody just comes up with a specific constraint, a specific operation, that I might be able to say like whether it can be simulated or not. But yeah, so I mean, like, maybe more on the side of applications. So for example, like I've mentioned several applications already, like the sanitizers, also the template stuff, right? And you might also be able to like do some kind of applications to so some replacement operation for in bioinformatics as well. So that's all I can say. Yeah.
Quick question. The ReplaceAll, is that a deterministic function? Because in general, actually, I would imagine it's non-deterministic. Like if you take ReplaceAll of 2 A's in a string of 3 A's.
It's a very good question. So I think I mentioned that we take the leftmost longest match, so that makes it deterministic. It's a function.
So the finite state transducers you have there are deterministic then, or?
So we don't consider finite transducers, at least in this work. But so in general, if you want to model them as finite transducers, they're not always deterministic, but they actually give rise to a function. So.
I'm not sure this. Do you want to read this question before I read it out loud? Does that question make sense?
Which one? The last one?
Yeah. We should make sure. I want to make sure it's not for the other session.
Okay. The set of models of logic regular context-free languages. Oh, I don't know.
Okay, well, let's read that one. It'll save you.
All right, okay.
Okay, so if you have more questions, please catch Anthony at lunch.
All right, thank you so much.
One more time.
Thanks.